Hi, I'm Mr. Rothwell. Today on Real Chemistry with Rothwell, we'll be discussing electron configurations, and I'll show you a few tricks for doing electron configurations consistently and well up through barium. In order to write electron configurations, I make a diagram which will tell me which subshells will fill earliest because they have the lowest energy. In order to do this, I start by writing the numbers 1 through 7 with an S afterwards, and I stack these vertically. After I do that, I do the same thing except with P, and I start at 2. I do the same thing with D, except I start at 3. And finally, the same with F, except I start at 4. Now already this diagram is useful because it tells me the type of subshells that exist at the different energy levels. In the first energy level, there's S. In the second energy level, there's S and P. And in the third energy level, there's S, P, and D subshells. But to make this thing more useful, I can draw arrows back and to the left through the numbers carefully. Now, if I read the arrows, I can see that if I start at the top and read back into the left, the first subshell that I'll encounter is 1s. If I jump down to the next arrow, it's 2s, then 2p, and then 3s, and you get the idea. So I just read back into the left and down the arrows. The best part about this is that the first subshell that I encounter is the lowest energy, then 2s is second lowest, and then 2p is third lowest, and so on and so forth. So it tells me the order that I fill in. So when I have an element and I want to place its electrons, all I do is I place the electrons in the lowest possible subshell first, and then I fill those until I get to the next subshell, and then I keep doing that. So I would fill 1s, then 2s, then 2p, until I got however many number of electrons I needed to situated. If I remember that S subshells can hold 2 electrons, P subshells can hold 6 electrons, and D subshells can hold 10 electrons. Finally, F subshells can hold 14 electrons. I can completely fill the subshells and then move on to the next subshells. For example, if I want to do the electron configuration for silicon, if I look at silicon, I see that its atomic number is 14, meaning it has 14 protons. So it also has 14 electrons if it's neutral to cancel out the positive charge of those protons. I need to find a home for all 14 of the electrons, and the way I do it is I'd use our figure. Silicon, and I'll make a note, has 14 electrons. So if I read down the chart and down the arrows, I'm going to fill every single subshell to find a home for those 14 electrons. And until I've done so, I'm going to keep going. Silicon's electron configuration is 1s2, 2s2, 2p6, 3s2, 3p2. Now you'll notice that I have filled every single subshell with the maximum number of electrons. However, by the time that I get to 3p, I notice that although I can hold 6 electrons, I only have 2 left. Looking at the superscripts, 2 plus 2 plus 6 plus 2 is 12, so I only need to find the home for 2 more. So although I have room for 6, I only put 2 there because I only need to house 14 electrons. It's similar to going to a restaurant and having a party of 3, and they put you at a table suited for 6. If you only have 3 people, well, then the 3 of you sit down comfortably. Now you'll notice that I said that it works almost every time. In reality, there are 2 exceptions between hydrogen, which is element number 1, and barium, which is element number 56. The first one would be chromium. Chromium has 24 electrons, and its electron configuration actually looks like this. So we have chromium, and its electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5. Now, what makes this unique about chromium is if you look here, you actually don't fill up 4s before you begin filling 3d. Now, this has to do with the stability of the atom and the fact that if you have 1 electron in all 5 of the d orbitals, then it's stable. But most notably, we just want to point out that it is an exception to the rule. The other exception to the rule would be our pal copper, who has 29 electrons. And so it's very similar to chromium in the sense that it starts by filling up all of its lowest energy sublevels first. But then it does a very similar thing to chromium in the sense that it does not completely fill the 4s subshell before moving on to the 3d subshell, which technically comes later in our diagram. However, it adds stability to have a completely full third energy level for copper, so it will opt to do that. Again, these are the big two exceptions between hydrogen and barium, and if you have these down, then you've got the first 56 elements down for electron configurations. Thank you for listening to another episode of Real Chemistry with Rothwell.